Let's do another work energy problem here. So this one, it says there is a small box of mass m that's given a speed of the square root of 1/4 g times r at the top of the smooth half cylinder, so it's smooth, no friction. We want to find the angle theta at which the box leaves the surface. All right, and this is from the Hibbeler textbook, by the way. It's like 14.16, I think. Now, what I'm going to do first is I'm going to draw the free body diagram. All right, so let's draw the free body diagram, and I'm going to draw it when it's, over here, because that's kind of the point we're looking at. So there's my box, and let's put our forces on here. Well, I know I'm going to have a weight, right? Goes straight down, and then we would have this normal force. Okay, now notice that this is a curved path that we're on, right? It's not a rectilinear motion type problem where we have a straight path, because this is curved, so it's curvilinear. So because of that, I am going to set up my coordinate frame to where this is n, and then this is t. All right, so we've got that, and then if we were to look, this here is going to be theta, which means this is theta. Okay, so now we've got that. Now we're going to use work energy, like I said, to do this. So which of these forces is going to do work? Well, it's just going to be the weight, right? Because remember, for work to be done, we have to have a displacement in the exact same direction as the force. I do not have a displacement in this direction here, right? We don't have that. So work is going to be done by weight only. So let's kind of write that out. So we'll just say the weight has work, and let's call it UW, I guess. So UW is going to be the force, which is m times g, and then we need the distance that is traveled, basically, in this direction, or in a vertical direction. Okay, so I'm starting up here. Here's that block. We're starting there, and then we're going down to this point. So this point right here is going to be the point where this starts to leave the surface. So basically, if I drag this line over here, this is the distance that I need, right? Because I need to know how much we dropped in height. Okay, so that's going to be our distance. Now, if we look, this distance here, we could say that's r, and then if we draw this over again, this right here, that's going to be r cosine theta, right? So I can take the difference of those, and then that's going to give me this little distance here, the distance that the box dropped in the vertical direction. So that's what we're going to do for our distance. So we're going to have r minus r cosine theta. And this one's going to be positive because the weight and then the decrease in altitude, those are in the same direction, right? The displacement's going down. So that'll be positive. Now, I know that work has to equal the change in kinetic energy, right? So T2 minus T1, essentially. And T is the notation that Hibbeler book uses for kinetic energy. I know some other books use different notation, but T is kinetic energy. So now what we need to do, we're going to take our work equation right here, we're going to put it on the left, and then we're going to do the kinetic energy part. So let's have mg times r minus r cosine theta, and then that is going to equal 1/2 m times v2 squared, right? And then minus 1/2 m times v1 squared. Now, do I know v1? I do know v1, right? It's right here. So that means we can take this and plug it in for v1. All right, so if we do that, I kind of rewrite this out so we can show that. So if we do that, then we're going to have minus 1/2 m times the square root of 1/4 g times r, but we're taking the square of that, right? So we square that, that's going to get rid of that square root. Now also notice I've got m here, here, and here, so all of those will cancel out. So mass goes away, and then let's expand this out on the right or left side. So we have gr minus gr cosine theta, and then that's going to equal 1/2 v2 squared minus 1/8 GR. Right, so that's what you'll get after we square this, get rid of the square root. So basically you'll have 1/2 times 1/4, that gives us the 1/8. And then the m was canceled, right? So now we've got this. We need to solve for v2 because that's what I'm looking for, right? I need to know the speed right here when we're going to leave the surface. So let's go ahead and solve for v2. And we'll just leave it as v2 squared for right now. And that is going to end up being 9/4 times gr minus 2gr cosine theta. Right, so that's what you'll get after you do the algebra there. Now, what am I going to do with this? I'm looking for this angle theta, right? That's what we're looking for. I've got an equation for the speed where we're going to leave the surface. Okay, so what I'm going to do is basically do Newton's second law, and I'm going to use this n and t coordinate frame, right? And I've got v squared, so that means I want to use the n component. So let's do the sum of the forces in the n direction. N towards the center of curvature is positive. We know this has to equal MAN. Remember what AN is. It's v squared over rho, right? I already have my equation for v squared right here. So I can take this and plug it in right there. Okay. Now let's look at the forces in the n direction. So obviously there's an n right here. Let's write it down. We're going to change it in just a second, but let's put a positive n, and then the weight has a component in the n direction going downward like this. So that's going to be mg cosine theta, and that'll be positive. So that's what we're going to have there, and we're going to set that equal to mv squared over rho. Actually, let's not make it rho. Let's use this r because that's what they have here. It'll be better. All right, there we go. So now we've got that. Now what should we do with n? Because it says the box is going to leave the surface, right? So we want the angle theta in which the box leaves the surface. So that means this needs to be 0, because if we leave the surface, we don't have a normal force, right? So that's going to go to 0. And now let's plug in our equation for v squared. And before we do that, notice the m's here cancel. So that's going to give us g cosine theta equals the v squared. So that is the 9/4 g times r minus 2gr cosine theta. We're going to put that over r. And then a bunch of stuff cancels, right? So if we look, the r's here will cancel. So those go away, and then the g's all cancel out right there, leaving us with cosine theta equals 9/4 minus 2 cosine theta. Right? So we can group up the cosine terms. So move the negative 2 cosine theta over. That gives us 3 cosine theta equals 9/4. And then you can solve for your theta, and you get 41.41 degrees. Right? So that's the angle that we need to be at in order for the box to leave the surface. Okay, so we kind of combined normal tangential coordinates with Newton's second law, along with work energy to solve that. So kind of a bunch of little topics thrown into one problem there. All right, hopefully you like that one. I'll see y'all for the next one next time.